Hello and welcome to Wednesday lecture, first week Wednesday lecture for Chem 106. Hopefully you guys found the first lecture as something that you could actually view or download or something to that effect. If you have had any problems with that, please let me know. Um, I wanted to just kind of do a real brief introduction before we actually start talking about some real organic chemistry, some real science. One thing is I'm going to do my best to kind of keep these videos around like 20 to 25 minutes or so, just to kind of make them a fairly manageable thing for you guys to do on a given day. Also, underneath where you found this video, there should be a section on Canvas labeled resource guides. This is where I'm going to post some things that I typically use as handouts in class, things that just kind of help to organize notes or summarize things that I'm talking about. So I kind of envision you printing those out or at least having them available and kind of filling them out as you go through the lecture. So without further ado, let's talk about some organic chemistry. As I've said previously, Chem 106 is going to be basically an introduction to organic chemistry and also biochemistry. So it'd probably be a good idea if we defined what organic chemistry was. I'm sure you've heard the word organic before, but generally that is kind of an everyday speak, something that's more a nutrition type food. Organic chemistry, it turns out, is very specifically the chemistry of compounds that contain chains of carbon and hydrogen, and that kind of serves as the backbone for a whole bunch of different compounds, actually an infinite number of compounds. But the really exciting stuff happens when we start to include oxygen, nitrogen, and other atoms, and that leads to something called functional groups. We'll talk about a couple of the fairly simple functional groups today that are just made up of carbon and hydrogen. But most of the more exciting ones, like for instance, ones that are present in like medicinal drugs and things like that, contain oxygen, nitrogen, and such. In fact, we're big giant chains of carbon with a little bit of oxygen, nitrogen thrown in. So the first thing you have to recognize is that we're going to kind of learn a whole entire different language. Probably the most important thing to recognize at this point is one of the things you'll notice is that anytime you talk about a organic compound, first of all, they start with what's called a prefix. In this case, that meth is an example of a prefix. I'm sure you've heard that before, like methamphetamine. Turns out you put a methyl group on amphetamine. So the question is, what is that? What is that referring to? Well, it turns out anytime you see that meth prefix, that involves a single carbon. In this particular compound, since methane doesn't have any other kind of functional groups, nothing too exciting, it ends in an ANE. So ANE is kind of like the non-sexy ending in organic chemistry. It basically just says that there's nothing interesting in a compound, and typically these things are just burned. For instance, natural gas has a bunch of methane in it. You'll notice here that ethane, that the ETH corresponds to something with two carbons in a line. Once again, nothing too exciting happening there, so it just ends in ANE. Prop is going to be associated with 3. I'm sure you've heard of propane before. Liquefied propane is what comes in those tanks that you get at the supermarket. And then, of course, we've got butane, like would be present in a butane lighter. So anytime you've got 4 carbons stuck together, that's called a but group or but prefix. And if it ends in ANE, there's nothing too interesting happening in there. Hydrocarbons is one of the kind of vocabulary words that is pretty obvious, is that a hydrocarbon is anything that contains hydrogen and carbon. And these are going to be kind of the backbone of everything that we talk about in this introduction to organic chemistry. A couple of things you should remember is this idea of covalent bonding. And so what is true between all these carbons and all these hydrogens and carbons is that they're all covalently bonded compounds. So this whole idea of like methyl, ethyl, propyl, and butyl, it turns out that we could talk about a whole bunch of other prefixes I would say probably starting now memorizing these four is a really good idea. I always think of the prefix monkeys eat peeled bananas. We will talk about naming organic compounds probably on Friday, but that's kind of a good start getting those guys memorized. So there are other prefixes. Pent usually is something that's associated with 5, and then hex is 6. And then, of course, we could go absolutely crazy. I will say that on any test, I'll give you anything greater than 4. You memorize the first 4, and anything greater than that, I'll give you the name of the prefix. So you can see, like, for instance, the oct corresponds to 8. You could probably figure that out. There's a bunch of kind of unusual ones when you look at undecane and dodecane and tridec. And there's all kinds of unusual larger chain hydrocarbons. One of the things that happens as you extend these chains, and by the way, this is going to be something that we do, we'll usually introduce organic chemistry by introducing kind of the structural motif that is the most common, and then we'll go through and we'll talk a little bit about physical properties, things like boiling points, things like melting points, things like densities and stuff like that. And then we'll eventually talk a little bit about what I really think is exciting, and that's the actual chemistry, whether that chemistry is something that happens in a test tube, or that chemistry that happens in the human body. You can probably tell from this next slide something about the physical property of hydrocarbons. You notice that we've got this gasoline here. We've got diesel, we've got motor oil, and you've got plastic. One of the things that you'll notice between these is you move from something that's, a liquid, but really kind of wants to be a gas. And then you get to something like diesel, and it gets a little bit viscous, and it's a lot harder to burn. I can't remember if I ever did my demo with diesel and gasoline for you guys. But it's a fun one for sure. And then, of course, you've got something like motor oil, where you've got a bunch of different carbons connected together. And it turns out basically all plastic is the solid phase thing, right? We've actually moved into the solid phase at at room temperatures and pressures. And all plastic is a big, giant, long polymer chain, and we'll actually talk about polymers specifically on Monday, at least hydrocarbon polymers. So these are all different types of hydrocarbons. One of the things you should always know about the physical properties of hydrocarbons, they're always non-polar. And you can kind of remind yourself of that whole expression that water and oil never mixes. Well, the reason that those things don't mix is that water is polar and all hydrocarbons are non-polar, and all oil is big giant chain of carbons. Another thing that you should probably know is the larger the chain, the higher the boiling point. We see that on this particular slide. And it's also a good idea to remind yourselves from Chem 105 that the only thing that nonpolar compounds have available in terms of an intermolecular force is called a London dispersion force, LDF forces, also called instantaneous dipole. So if you don't remember what that is or how to recognize it, might not be a bad idea to review a couple of your notes from Chem 105. So one other thing that is true of hydrocarbons, you might notice that when we talked about refined petroleum, for instance, what they're typically talking about is some sort of distillation, where what you do is you take some crude oil out of the ground, and what you end up doing is it's kind of in a state that crude oil is in a state where all the different hydrocarbons are all kind of mixed together. And so what you do is you put them in a distillation tower, you heat the bejesus out of it and pressurize it. And what you'll notice about this is that the really, really high hydrocarbons are something that you kind of remove from the bottom of the still. And then as you get up here, you'll notice that you get smaller and smaller hydrocarbons. And so you end up with, just kind of like more household substances here. I remember one thing that was always true is that my dad, whenever he'd work on a car, he'd always like coat his hands in kerosene to get all the grease off. Well, the grease from the engine was made of, like, basically a whole bunch of carbons, so it would make sense that he'd use something that was in the liquid phase to get those carbon molecules dissolved off of him. Problem is, he always stunk. But yeah. So that's just a little look at the way that the crude oil is basically just a whole bunch of different mixture of hydrocarbons. Has a little bit to do with the physical property of hydrocarbons. Just kind of an interesting thing to know. Another thing which you should be aware of is this idea of structural isomerism. I'll probably insert like a little whiteboard talk in here as I go back and edit the slides. So this idea of structural isomers, they're compounds that have the same chemical formula but different connectivities. I kind of think about this as if you get up to a certain size of carbons, you actually have the opportunity to kind of connect those Legos together in different ways. In fact, in GS 105 last year, we just thought about these things as Legos. So a great example of that is on this next slide. Different isomers of pentane are possible. So here is a single isomer of pentane. It's called, well, it's just regular pentane. It's linear pentane, sometimes called N-pentane or normal pentane. But it turns out that you can actually have an isomer of pentane where you take one of these methyl groups, pop off a bond, and then stick it in one of these interior carbons. Turns out this thing right here, which is called 2-methylbutane, some people call it isopentane. But one of the things that's true of this is it has completely different chemical reactivity, physical properties, things like that, than the original isomer here. So you can kind of count up the number of carbons and the number of hydrogens in both of these. You'll actually find out that they're exactly the same number of carbons and hydrogens, but it's actually a completely different compound. We also have this thing, which is called Neopentane. This is something that has the same number of carbons and hydrogens, but obviously you've kind of started to take apart those Legos and connected them together a little differently. And then I'm gonna skip this very next slide because it is actually not an isomer of pentane. Well, I shouldn't skip it. I'll show it to you, but this is actually not technically an isomer of pentane because it has a different number of hydrogens. But this thing just kind of shows you that it's possible for carbons to kind of bite their tail and end up with what's called a cyclic structure. Turns out in this case that is not an isomer of pentane, because if you add up the number of carbons and hydrogens, turns out that they're not the same as the other three. So one thing that I wanted to talk to you a little bit more about is this idea of structural isomerism. Sometimes, by the way, books will define these as constitutional isomers. But what I did was I just showed you a particular compound, and I wanted to show you how this idea of structural isomerism works out. One of the things that you'll notice about this structural isomer, by the way, this is acetone, also known as 2-propanone. But one of the things that is true of this compound is that it requires you to have 3 carbons, 6 hydrogens, and 1 oxygen, right? And it turns out that any different way that we can connect together all these different Lego pieces, it turns out if we end up with different compounds, those are going to be considered structural isomers, right? But the one thing that must be true is that if something that I write is truly going to be a structural isomer of acetone, what must be true is that I have to use all of those carbons, I have to use all those hydrogens, I have to use all those oxygens, I can't use any more or any less. So couple of ways that you can kind of put all this together. By the way, we'll kind of learn as we go how to use what's called condensed structural drawing, which I'm kind of using right now. I'm not showing each individual hydrogen bonded to the carbons. I'm kind of grouping them together.
And what I'll do is I'll show you a different way that all of these could come together. Oops, I'm running out of space. That, it turns out, is considered a structural isomer of acetone. This is actually called propanal. It's called an aldehyde, a different kind of functional group. But one of the things that you'll notice about that is that we've got everything that we need, right? We've got 3 carbons, right? If you count up all the hydrogens, we've got 6, and then there's 1 oxygen. And it actually turns out that we can even be a little bit more creative with this. Another type of structural isomer of this thing, and keep in mind, I can keep, as long as I use 3 carbons, 6 hydrogens, and 1 oxygen, that anything I draw is technically a structural isomer of this acetone. So another way that we could kind of think about connecting all these guys together, well, turns out we could draw something like this. There's an example of an alcohol. But once again, you'll notice we've got 3 carbons, a total of 6 hydrogens, and 1 oxygen. And this is an example of something that has an alcohol functional group and also that alkene that we talked about. Right? And so I just show you this as kind of like an introduction to this idea of structural isomerism, that honestly, as long as you can, recognize a molecular formula, this being a molecular formula right here. Oops, let's try that again. So as long as we have that, yeah, you get the idea. As long as we have that formula, that's considered a structural isomer.
So, another thing which you should know, oh, by the way, don't forget about your resource guide where I kind of help you guys out by giving you a kind of a note-taking guide. There's a couple of different types of hydrocarbons that you should know about. One is this idea of being a saturated hydrocarbon. And saturated hydrocarbons are differentiated from unsaturated hydrocarbons because in a saturated hydrocarbon, you basically take that carbon and you attach as many H's as possible. One thing that's super important to remember in organic chemistry is that carbon bonds 4 times. Once again, I will say it again because it is absolutely essential that you know that carbon covalently bonds 4 times in order to satisfy its octet rule. A couple of different types of saturated hydrocarbons we've already seen, right? We've seen our meth, eth, prop, bute kind of series right there. You'll remember that they all end in ANE. And that's going to be a little bit different when we get over here to the unsaturated hydrocarbon area, because it turns out when you're an unsaturated hydrocarbon, technically more H's could be bonded. And this gives rise to our very first functional groups. And those functional groups are alkenes, alkynes, and aromatic compounds. So we're just going to take a little time and take a look at each of these. So one of the things that is true of all unsaturated hydrocarbons is that they contain double or triple carbon-carbon bonds. So here are 2 examples of something that is considered an alkene, right? And one of the things you'll notice right away is that the ending is very different, right? We had eth that corresponds to 2 carbons, and then the ene is something that indicates that this actually has some sort of carbon-carbon double bond. Propane much the same, ends up with 3 carbons bonded together. The ENE ending corresponds to that double bond right there. And as I said, we'll name more complex ones as we go on. So here's just kind of a summary slide talking about the different types of unsaturated hydrocarbons. Well, we said that alkenes, they have to contain 1 or more CC double bonds. We have alkynes, which we haven't seen yet, but these contain 1 or more CC triple bonds. So something like that. And so what do you think that would be called? So what we would do if we wanted to name this, we would say, well, how many carbons are in a line? So I've got 1, 2, 3, 4, 5, 6. And we would look at the guide we saw in a previous slide. And we would say, well, 6 carbons, that must be a hex. The fact that this has a triple bond is going to make this sucker end in a YNE. So this is an example of a hexyne. And one of the things you'll notice is that it is kind of in the middle here. So it turns out that that triple bond could have conceivably been on any of these carbons. This one, though, is going to be called a 3-hexyne. So that might give you a little bit of insight into how we name these things, right? The 3 corresponds to the fact that it's on the 1, 2, 3rd carbon. So this would be an example of a 3-hexyne. As I said, on Friday we'll talk a lot more about naming, and a couple of your resource guides on Friday are going to have you practice with naming a couple of compounds. So we've got one other type of unsaturated hydrocarbon, which is a pretty special one. Those things are called aromatics. They contain 1 or more what's called a benzene ring. These are all over the place. They're in our bodies, they're in plants, they're in the ground, they're absolutely everywhere. Benzene rings have this kind of structure. You'll notice that it's this like perfectly cyclic 6-membered ring, and there's these what's called alternating double bonds here, but it turns out these aren't really double bonds. It turns out that this thing undergoes what's called resonance, and so it turns out that these are all equivalent, right? And this little arrow right here, which we're not going to talk much about, this is called a resonance arrow, and this is basically saying that benzene exists as kind of both of these together at the same time. It's almost like we're not allowed to call something blue and, I'm sorry, that we're not allowed to call something green, right? It's like we have to represent the color green as blue and yellow 50%, right? You know what I'm saying? We have to like imagine that it's actually kind of a mixture of both of these. So like you would represent green as like blue and yellow with this little double arrow. So because of the fact that this thing exists as in those resonance forms, you'll often see benzene represented like this, which shows you kind of that all those double bonds are actually equivalent. They're actually not even double bonds. They're more like bonds and a half if you really want to think about it that way. But it turns out that this structure is pretty important. It's a really, really planar structure. So it just kind of, sits on a table basically, like if you imagine it. It doesn't have any kinks in the chain. There's a picture of what it looks like. You can kind of see that nice flat plane. It turns out it's incredibly stable. And it's something we, if we were in a 200 level organic class, we would talk about a whole bunch. Other aromatics, you'll notice that they kind of have a similar structure on this next slide right here. I always include naphthalene because it reminds me of my grandmother. My grandmother always had mothballs in the closet. So mothballs actually have naphthalene as a way to like repel the moths that used to eat sweaters. I guess they still do. But this is a structure of naphthalene, and you can kind of see these other aromatic compounds. Actually, interesting story about the benzene ring with like 4. Of course, you can get ones with 5 and 6 and anything else. Those polyaromatic hydrocarbons are actually what makes charbroiled food, barbecued food so good when you use like charcoal bricks and stuff like that. One of the problems with a lot of these organic things, or sorry, a lot of these aromatic things, is that they actually do what's called intercalating into DNA because they're so incredibly flat. So it turns out that these like polyaromatics right here kind of fit perfectly in between your DNA base pairs, and they can cause mutations and stuff like that. So it's really sad because, man, that barbecue that has the charcoal bricks, so much better tasting than something cooked with like a propane grill. So, but you know, anything in moderation. Um, so I think that's just about all I wanted to talk about today. As I said, I'm going to try my best to keep these lectures like between 20 and 25 minutes. So this one is probably going to be, you know, mid 20s. I think I'll go ahead and stop here. So I look forward to seeing you on Friday. Don't forget about the celebration of new knowledge. Remember, those are going to be something you have to do every Monday, Wednesday, and Friday after viewing these lecture slides. And I will talk to you again on Friday.